Hi everyone, and welcome to this short video about basic integration. In this video, we will finally learn how to calculate integrals. We will start with the fundamental theorem of calculus, which is the base for integrating. Then we will talk about the concept of antiderivatives and how to calculate them. At the end, you will be able to calculate integrals on your own and can test your knowledge in several exercises at the end of this video. Let's start with the fundamental theorem of calculus. The fundamental theorem of calculus links the concepts of differentiation and integration. It explains to us how we can calculate integrals, which is why we are especially interested in it. The theorem consists of two parts. The first one tells us something about the relation between derivatives and antiderivatives, and the second one then links antiderivatives and integrals, and finally tells us how we can calculate those. Let's start with the first part. The first part of the fundamental theorem of calculus goes as follows. Let f be a real-valued continuous function on the closed interval ab. Let f, so here capital F, be a function on the same interval, and we have an x that is element of that interval. We define the function f of x, so capital F here again, as the integral from a to x of the function f of t dt. The function f is differentiable, and the following relation here holds. The derivative of the function capital F of x is equal to the function f of x for all x. We call the function capital F the antiderivative of the function f. Let's take this apart and understand the meaning. So we have two functions, the small f and the capital F. Both are defined on the interval ab and mapped to the real numbers. Now, if the derivative of the capital F function is equal to the lower f function, the capital F is called the antiderivative. So capital F is like the opposite of the derivative of the small f, because the relation goes in the other direction. But there was also more to the definition on the last slide, so let us take a look at that now. The antiderivative capital F of x was defined as this integral. So in summary, it describes the integral from the beginning of the interval, which was a in our case, to any point x, which is somewhere on this interval. This is a very interesting relation, so let us take this further. Up till now, we still don't know how to calculate an integral on our own for any two borders. So this is where we need the second part of the fundamental theorem of calculus. The second part of the fundamental theorem of calculus is the one that finally tells us how to calculate integrals. It states that the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. So in other words, it is equal to the antiderivative of b minus the antiderivative of a. So this is the solution to calculating integrals. All we need to do is finding the antiderivative of a function we want to integrate, and then we need to plug in the limits a and b. The total integral is then calculated by subtracting the antiderivative plugged in with b, and then subtracting from it the antiderivative plugged in with a. Seems like a nice formula, so let us take a look at this in a visual relation. Here you can see a graph of the function f of x on the left side, and a graph of the function capital F of x, which is the antiderivative of f of x, on the right side. Note that the scales here don't match, but this is just to give you a visual intuition. On the bottom left, we can see different borders, which are 0, which is the beginning of the interval on which our function is mapping, a, which is somewhere in the middle, and b, which is more to the right. You could now imagine the three cases of calculating the integral from 0 to a, from 0 to b, or from a to b. The integral from 0 to a is colored in orange, the one from a to b in green, and the one from 0 to b would be both parts together, marked in pink here. Now on the bottom right, you can see the antiderivative. At any given point, it gives us the number of the integral from the beginning of the interval we map from, which is 0 here, to any x value. Therefore, at the location x equals a, capital F yields the integral of our function lower f of x from 0 to a. And the same holds for the location b. The integral from 0 to b of the function f of x dx is equal to the antiderivative, capital F, of b, so at the location x equals b. Therefore, it is also logical that the integral from a to b is the difference, capital F of b, minus capital F of a. Because we are precisely only interested in that part, the part between a and b, and nothing that comes before or after. So far about the visual intuition, but let us bring this theory to practice now. You already get to know the formula for integrating, but when you apply it in practice, this is the common notation. You start with the integral sign, which is this curved line, and write the left or lower limit below and the right or upper limit above. Behind that, you write your function f of x and the dx. In the next step, you use the squared brackets. Inside of these squared brackets, you write the antiderivative of your respective functions. The limits are still kept, but now you write them behind the squared brackets. The upper one on top and the lower one on the bottom. And finally, you can continue with setting the limit values inside the antiderivative and subtracting them. And that is already it for the notation part. So, in summary, when you want to calculate an integral, you have to perform the following steps. First, you need to find the antiderivative of your function. After you've found it, you can plug in the limits for x and then subtract f of a from f of b. The result will then be your integral. Here I have two examples for you. We have the integral from 0 to 3 and the integral from 1 to 5 of the function f of x. As f of x, we will use the function from the graph you saw on slide 7, which was f of x equals x. With the notation from the last slide, you should now be able to calculate the integrals. As a hint, the antiderivative was also given on slide 7. It is 0.5x to the power of 2. We will go through the solution to these two tasks together in a second. Here you can see the solution to the two tasks. Let's discuss them together. In the first example, we had the integral from 0 to 3 of f of x dx. In the first step, we will replace the f of x by our function. In our case, this is simply x. So now we have the integral from 0 to 3 of x dx. In the next step, we will calculate our antiderivative and place it inside of the squared brackets, as you have seen it on slide 8. Luckily, the antiderivative was already given, so we can simply use it here. The limits are kept, and therefore we now have 0.5x to the power of 2 in squared brackets, and the limits 3 and 0. In the next step, we need to plug in our limits. We always start with the upper limit, which is a 3 in our case. If we plug it inside of our antiderivative, we will get 0.5 times 3 to the power of 2. Now we do the same with the lower limit and subtract it. So we have minus 0.5 times 0 to the power of 2. In total, this will be 4.5. In the second example, there's not much different, because we had the same function f of x. Therefore, the antiderivative is also the same. The only difference here is that we have different limits, so instead of 3 and 0, we will use 5 and 1 here. This yields 0.5 times 5 to the power of 2 minus 0.5 times 1 to the power of 2, which is 12 in total. As you just saw, all you had to do was plugging in values into the antiderivative. Seems nice, but what do you do when the antiderivative is not already given, like in the examples you just saw? Antiderivatives are a crucial part for integrating, and therefore we need them. The solution is therefore, we calculate them on our own. You already saw the definition of an antiderivative earlier. It is defined that if you take the derivative of the antiderivative, this will yield your normal function again. So the derivative of capital F of x is equal to small f of x. And therefore we need to do the opposite of derivation. Here you can see the most important rules for finding antiderivatives. It is like finding a derivative, but the other way around. The most important rule is the first one. It shows you how to find the antiderivative of x to the power of n. The antiderivative here is 1 divided by n plus 1 times x to the power of n plus 1. If you think about the relation between derivative and antiderivative again, this makes sense. If you would derive 1 divided by n plus 1 times x to the power of n plus 1, you would have n plus 1 divided by n plus 1 times x to the power of n, which is the same as x to the power of n. One exception is when n is minus 1. This would mean x to the power of minus 1, which is equal to 1 divided by x. In this case, the antiderivative is ln x. The other rules should also look somewhat familiar to you, just that you know them the other way around from derivation. Note that these are of course not all rules, but the most important ones. Another thing worth to mention is that you can always add a constant c to the antiderivative. This is the case because it will fall away when you derive it again. Therefore, a function has infinitely many antiderivatives. You might now wonder why this does not affect our integral when there are infinitely many different antiderivatives that we could use. The answer is, when calculating an integral, you subtract the antiderivative from itself, just that you plug in once the right limit and once the left limit. For a constant, this would of course cancel out each other, because c minus c is always 0, independent of the value we choose for c. Therefore, for practical reasons, we usually simply set c to 0. And that's already it for all the rules and formulas in this presentation. Let's continue with some exercises. Here you can test your new knowledge from this video. In task 1, you're supposed to calculate antiderivatives. In task 2, you should calculate two integrals. You can pause the video now. The solutions can then be found on the next slide. Here you go with the solutions to the exercises. In task 1, you had to apply the rules for finding antiderivatives. In all three cases, you can use the first rule from slide 12. The trickiest one here is h of x, because x is written below in the fraction. But you can easily rewrite it and then apply the rule. In the second exercise, you were supposed to calculate integrals. And then you can follow the step-by-step explanation on slide 8. First, you need to find the antiderivative, which can be calculated with the help of the rules. And then you need to plug in the limits and subtract it. The results will be 316 for the first integral and 2 for the second one. And that's already it for this video about basic integration. By now, you should be familiar with how to build antiderivatives and how to calculate integrals on your own. I hope you like this one and see you again next time.